the morning session today. We are very honored to invite Professor Jianfeng Lin from Tsinghua University. He will talk about configuration spaces and diffeomorphism groups of four manifolds. As welcome.
Thanks very much for the invitation. It's my great pleasure and honor to speak at SBS 2025. And today I want to talk about the main focus today is about the diffeomorphism group of four-dimensional manifolds. So basically, we'll try to understand the symmetry on manifolds. And maybe let's start by reviewing some relevant definitions. So let's say M is a smooth manifold. Throughout the talk, we'll assume M is compact oriented, but we do allow M to have a boundary. Okay, and we consider the group of orientation preserving diffeomorphisms. And when M has a non-empty boundary, we require that the diffeomorphism must be identity on the boundary. Okay? And this is not just a group. Actually, we can equip this group with smooth C infinity topology, meaning that a sequence of diffeomorphism converge has a limit if all its derivatives converge uniformly to that limit. Okay? So that's the C infinity topology. So using this topology, we can make this group into a topological group. So it is a group with a topological structure. And we hope to understand these objects from two perspectives, at least. Of course, there are more perspectives. The first perspective is through algebraic property. Namely, we want to study like group theoretic property of this diffeomorphism group. Say we want to understand its subgroup, we want to understand its quotient group, and we want to understand whether it's a simple group, and we want to understand, for example, what's the abelianization of this group. So these are all group theoretic properties. And the second perspective is to study its topological property. Namely, we want to understand its property as a topological space. In particular, we want to at least partially understand its homotopy type. For example, how many path components does it have, and what's the homotopy type, and how to compute the homology of the diffeomorphism group or its classified space. Okay, so these are two different perspectives. Well, of course, they are quite closely related, as we will see. But the main focus today is to study the topological properties of diffeomorphism group for four-dimensional manifolds. And you will see some interesting new phenomena happens in dimension 4 that doesn't happen in lower dimensions, as you will see. So maybe before talking about specific results, let's talk about some motivations. Why do we care about this object? Okay, so the first motivation is that understanding this diffeomorphism group helps us to classify manifolds, but not a single manifold. Rather, we want to classify a manifold in a family setting. So what does that mean? Okay. So, remember that given any topological group, G, you can define its classifying space, BG. So basically, you find you can find a contractible space with a free G action. You take the orbit space, that gives you the classifying space, BG. And over this BG, there is a universal bundle. Okay, so it's a fiber bundle with fiber M. M is our given manifold. And it's called universal because every smooth fiber bundle with given fiber M and with given base A, the isotopy class of all such bundle, one correspond to homotopy classes from the base A to your classified spaces. Okay, so if we try to classify all fiber bundles with fiber M and the base A, we are basically trying to classify families of manifolds parametrized by A. Right? So when A is a single point, of course, we're just trying to classify a single manifold. When, for example, you can consider more interesting cases. For example, A is a circle or A is a sphere. Okay? And also, another useful fact is that elements in this homology, in cohomology of this classified space, they correspond to characteristic classes of manifold bundles. Why is that? Because as we said, every bundle is pulled back from the universal bundle. So you just need to define the value of a characteristic class on the universal bundle as any element, any given element in this cohomology class, then you just pull back to a general bundle. Okay? And moreover, so this is one big reason why we want to understand the homology of this classifying space of diffm. And sometimes people working on manifold theory also call this BDFM the moduli space of M. Okay, so this is the moduli space in a smooth category. Yeah, well, of course, where M is a Riemann surface, this moduli space is not quite the same as the moduli space, for example, say for complex structures, but they are rationally equivalent to each other, meaning that if you just care about rational coefficient homology or homotopy groups, they're just the same thing. Okay? Right. Yeah, and also, if we want to understand, what do we want to understand? The homotopy group of this difff, because by this classification theorem, we see that if you want to classify manifold bundle over a sphere, that actually one corresponds to homotopy class of diffm. Okay? Say you want to classify like two-sphere bundle over a six-dimensional sphere, and you want to understand like pi 5 of diff S2. Basically something like that. Okay? Yeah. So and one more reason is that we can use this diffeomorphism group to understand some geometric structures on M. For example, as we will see, we can use it to understand like the space of smooth structures or the space of symplectic structures, as we will see later in the talk. Okay? So these are some motivations to study this diffeomorphism group. Basically, it's closely related to the classification problem for a family of manifolds. And also, another motivation is that it has some close connection with smooth structures. Okay, so let's introduce another topological group, namely the group of homeomorphisms. Okay, so homeomorphism do not require any smoothness. It just needs to be a continuous map whose inverse is also continuous. Okay, so this is another topological group. Now let's fix a given smooth structure on M. Then we have a forgetful map from the diffeomorphism group to the homeomorphism group, right? Because any diffeomorphism is just a homeomorphism. Okay, so this is a map, and so intuitively speaking, if you hope that the smooth structure on M is unique in some strong sense, you hope that this map is a homotopy equivalence, right? Because basically that means the symmetry, the automorphism, there are essentially no more homeomorphisms than diffeomorphisms, right? You hope that this is actually like the two categories are essentially equivalent to each other. Okay, and actually this intuition is correct. There is the following way to handle this problem. You know, in algebraic topology class, we know not every map is a fibration, but we can also replace the domain by some larger space and make it a fibration. Then we take the fiber of that fibration. That gives us the so-called homotopy fiber. Okay, so that's a homotopy fiber of this continuous map. And what do I want to say? This is the homotopy fiber of this map is actually homotopy equivalent to the so-called space of smooth structures. Okay, so namely, okay, so it's this notion is a little confusing when you first see it. Okay, so when we talk about smooth structures, what do we really mean? Okay, we can mean individual smooth structures, namely a set of compatible charts, right? A set of charts which are infinity compatible to each other. Okay, if you use this notion for smooth structure, then there are many smooth structures, and smooth structure is not a discrete object. It has a whole continuous space that parameterizes such smooth structures. But then, okay, then you start to ask, what do we mean by saying that S7 has 28 smooth structures? When we say that, we really mean S7. S7 has 28 smooth structure up to orientation preserving diffeomorphism. Okay? So if we quotient out orientation preserving diffeomorphism, then it becomes a discrete object. But if we just don't quotient that out, we get a whole space of smooth structures. Okay? And this map, the homotopy type of this space of smooth structure can be captured by studying this map. In particular, for example, if rho m is a homotopy equivalence, then the homotopy fiber is contractible. That means you don't have like fancy loop of smooth structures, of like non-trivial higher families of smooth structures. You don't have something like that. Okay? This is indeed true. So the natural question is this map a homotopy equivalence or not? The answer is yes, in dimension less equal than 3. So I think it's an old result by Cerf. This is also like when we say there are no essential difference between the smooth category and the topological category in dimension less equal than 3. This is a stronger statement than that. So basically, in a very strong homotopy theoretic sense, the two categories have no difference. Okay? Unfortunately, this result is not true in dimension 4, as I think it has been observed by many people. Donaldson, Friedman, Morgan, Ruberman, Barrelia, O'Connell, and use all these results use some gauge theoretic gauge theoretic techniques to prove the result. And yeah, sorry, I should also mention like Watanabe, so which prove a very important case that M is the four-dimensional sphere. Okay? And based on Watanabe's result, we actually we are able to develop some obstruction theory, and we prove that for any compact oriented for manifold, this map is not rationally two connected, meaning that a map is rationally two connected if it induces isomorphism on pi 2 and surjection on pi 3. But anyway, so it's not rationally connected. In particular, it's not a homotopy equivalence. So basically, we can see like a non-trivial family of smooth structures on arbitrary four manifolds. So this doesn't happen in dimension less equal than 3. And this result is proved by using configuration spaces. But this is not the main focus today. Maybe yeah, it's just part of our motivation. So yeah, another thing I want to talk about is studying embedding space of submanifolds. So this is another important topic in low-dimensional topology. So we have many different versions of embedding space. For example, we can study the original embedding space, namely just study all smooth embedding of a given manifold to another manifold. This is the most original one. And when M has a boundary, you start to hope we have some control on the boundary. So we impose this additional condition that it map boundary to boundary, okay? And the restriction of this map to the boundary is some given fixed embedding. So basically, we fix the boundary value and study what can change in the interior. Okay? So this is the second version. We want to fix something on the boundary. And there is the third version, which is the so-called framed embedding. So here, a framing in this context, it means a framing of a submanifold means a trivialization of its normal bundle. Okay? So in this space, you don't just have embedding, you also have a trivialization of the normal bundle of this embedding. Okay, so these are different versions of embedding spaces, and one big reason that we want to understand, we want to study such embedding space is we have the so-called we have this vibration. Okay, so the total space is the diffeomorphism rho on M, and it has a natural map to embedding because you can, for example, you fix arbitrary embedding I0, and then you can pre-compose any you can compose any diffeomorphism to get another embedding. Okay? So this is you have a natural map. It turns out that using this isotopy extension theorem, you can prove that this map is actually a fibration. So you take the fiber, you get all diffeomorphisms that acts as identity on this submanifold N, and also act as identity on its normal bundle. Then you can do a small rescaling trick to require that this diffeomorphism actually fix a whole tubular neighborhood of that submanifold. Then you just remove it and prove that the fiber is homotopy equivalent to the diffeomorphism group of the complement. Okay? So this is a very useful long exact sequence. In particular, that gives us the following map. You have if we have some manifold, and you consider pi 1, a loop of embedded submanifold, you can use this loop to produce a non-trivial diffeomorphism on the complement. So this sentence is very important. So yeah, it basically says a loop of embedded submanifold induces a diffeomorphism on its exterior. For example, I mean, maybe it's better to draw a schematic picture. Let's say you have, this is our M. It's a cylinder, and let's just consider our simplest case. A is a single point. Okay, then we can consider a loop, which is just like it goes around here. Then, if you think about what's the induced, then by applying this construction, we will get a diffeomorphism. We will get a diffeomorphism from this twice punctured disk to itself. Okay, and maybe it's an interesting exercise to see what this diffeomorphism is. Actually, you can try to figure this out by yourself. Okay? It's actually a composition of two Dehn twists. Right. Just think about like you have some. Yeah, I mean it's good to use isotopy extension theorem to see what happens. Really. Okay. Anyway, so this will be a useful map. We will consider it later. Okay, and another use of this submanifold is that if we can prove if we can find some submanifold N such that Fa is not isotopic to N, namely if we can find some submanifold such that our diffeomorphism move that submanifold essentially, then that implies the diffeomorphism is not isotopic to identity, right? Because isotopy extension theorem tells us that an isotopy of submanifold can always be extended to an isotopy of the ambient manifold. So these are two uses of embedded submanifolds. Any questions? Okay, so let's continue. Okay, now, so talking about submanifolds, I think we need to mention the very remarkable result by David Gabay, who was here last week and gave a wonderful talk. So Gabay actually a few years ago proved the so-called four-dimensional light bulb theorem. So maybe, okay, so yeah, so let me give its geometric statement first. Then I will explain why it is called a light bulb theorem. Okay? So let M be a four-dimensional manifold, and let's consider two embedded space. Okay, we let R be an embedded surface, and let G be an embedded sphere. Okay? Then we say G is a geometric dual of R if the self-intersection number of G equals 0, or you can say like the normal bundle of G is trivial, okay? And the G intersect R transversely at a single point. So basically, that's the geometric dual. So it's just a sphere with self-intersection 0 and intersect transversely at a single point with our given surface. Okay? And we also say R is G in essential if this technical condition, the fundamental group of the complement, the map between the fundamental group of complement is trivial. Okay. So here's the result by David Gabay. Given closed or embedded surfaces, given two embedded surfaces, R and R prime, which are homotopy to each other, suppose they have a common geometric dual G, then also assume the following two technical conditions. One is that fundamental group has no two torsion. Second, both R and R prime are G in essential. The second condition is empty condition if R is a sphere. because in that case the complement is just simply connected. But this condition is necessary when R has a genus. Okay, then the conclusion is that these two surfaces are isotopic to each other. Okay, so maybe I think it's better to explain some geometric intuition why it is called a four-dimensional light bulb theorem. Okay, so maybe let me also draw a picture here. First, maybe it's so let's think about the following space. Let's consider the three-dimensional version. So we consider the space of embedded arcs from S2 plus I. Okay, so you can actually prove that this space is path connected. Okay, and this is the traditional three-dimensional light bulb theorem. Why is that called light bulb theorem? Because if you think, let me just draw a picture. You have a roof, you have a light bulb. The cord is somehow knotted in some weird way. And this, okay. So here's the, then this is the light, this is the light bulb, and this is the cord. Okay. Now the question is, can you unwind, can you unwind this cord without moving this light bulb? Okay. Well, the answer is always yes, because you are allowed it to move this part of this arc below the light bulb and just change the crossing by this peak, right? So okay, of course, if you are allowed it to like drag it below and move it, well, I don't know, I draw bad pictures. Like you can move it like this and untwist this. So basically, this is a classical result. And basically, a special case of Gabai's four-dimensional light bulb theorem states that if you consider the embedding of, now we change this to two-dimensional disk to S2 plus D2. Okay, so if you do this, this is just Z. The only invariant is the relative homology class of this embedded disk. This is the analog. So basically, you see that you change from D2 to D1. So this is the 4D light bulb theorem. Okay. So why is it? So this is a breakthrough in four-dimensional topology. Why is that? Because this is one of the very few positive results in the past few decades. So a positive result. What do we mean by positive results? Okay. So there are two types of result. One type of result tries to define invariance and use invariance to distinguish different objects. Okay, so for example, in dimension 4, we can develop all kinds of invariants, some from gauge theory, and we can use this invariant to say, okay, two manifolds are not diffeomorphic to each other. Two embedded surfaces are not isotopic to each other. Basically, we compute the invariant, they are different, and we conclude that they are different. Okay? But that's a negative result. There are not so many positive results in four-dimensional smooth category. So positive result is like, okay, you just verify some abstract condition. Well, so you just verify some conditions, and then the theorem tell you that two manifolds are the same, or two submanifolds are isomorphic, something like that. Okay, that's called a positive result. So there are not so many positive results. For example, even nowadays, if we want to prove two four manifolds are diffeomorphic to each other, the only way is to construct the diffeomorphism by hand, basically. That's the only way we can. We don't have any like a general criterion, like if like the genus of two, some kind of genus of two manifolds are the same, they are diffeomorphic. We don't have something. We don't have anything like that for smooth four manifolds. But this is a positive result, right? You just verify these two conditions, and yeah, then the surface become isotopic. Okay, so a self-intersection number. So just perturb your submanifold so that it intersects transversely with itself. Then just count the intersection number by sign, plus minus sign. Just add them together. Deal? Oh well, it's because because of this condition. If you translate this two condition to cohomology, say that basically the Poincare ideal of G is the dual basis for the Poincare ideal of R. Yeah, so and also note that two torsion-free condition is necessary and it was discovered by Hannah Schwartz, and later this Leibov theorem was generalized to that situation by Schreiter Teichner. So they introduced another obstruction called Friedman-Quinn invariant. So yeah, okay. Then next I want to talk about, so since the Leibov theorem is so important, we want to generalize it in various directions. And I guess the first hope is to generalize it to disks. Okay? Instead of like closed surface, we want to study surfaces with boundary. And the first thing to study is like embedded disks. Okay? So before that, let's introduce a useful operation called self-referential. So what does that mean? So given a surface F, we can take a disk embedded in the complement of F. Then we take an arc connecting the boundary of this disk with this surface. Okay? So we take this arc satisfies some extra condition. For example, the interior of the arc must not intersect the disk and the surface, and it intersect the interior of the disk. The interior of the arc must not intersect the surface and the boundary of the disk, and it intersect the interior of the disk transversely at a single point. I mean, this looks again better with a picture, so let me draw a picture again. So what's that picture? So our picture is like this. Okay, we have a surface F. Okay, then we just draw some three-dimensional disk D. Okay, so that's the three-dimensional disk. And what do? We take an arc, maybe it's better with a color tool, like this, okay, which pass this disk transversely at a single point and go somewhere, and this is stop. Okay. So the point is that your manifold, we're living in a manifold, right? This is everything happens in a manifold. The manifold may not be simply connected, and you allow your disk, you allow your arc to travel along some holes. Okay. So that's a self-referential disk. And then what can we do? Okay, given such things, we can take a tube. We can take a tube. Basically, we take a small tube. This. Just take a small tube along this arc and do connected sum. So basically, connected sum means like we remove here, remove here. Okay, we can do this. By doing this, we create another surface called F prime. So F prime is basically the connected sum between the original surface F and the boundary of the three-dimensional sphere. So maybe I should draw, yeah, something like that. Okay, yeah. Okay. So we call this operation by adding a self-referential disk to our surface. Okay, and you can see that it changed the surface, but it's not hard to see that F prime is actually homotopy to F. It doesn't change the homotopy type of F. We will see that this operation often changes the isotopy type of F. I mean, this is not a very good picture because I should actually draw a three-dimensional ball here. This should be a three-dimensional ball rather than a two-dimensional disk. Yeah. Anyway, so yeah, so here is the result by Gabay. There exist two embedded disks into this four-dimensional manifold, such that the two disks have the same geometric dual. They are homotopic relative to boundary, but they are not isotopic to each other. Okay? So we will see that they are not isotopic because some invariant called the Dex invariant helps us to distinguish between them. Okay? And so what's the importance of this theorem? It tells us that four-dimensional light bulb theorem, if you want to generalize it to disks, you need a modification. At least you need to take the Dex invariant into account. Okay? So that invariant, I will talk more about this invariant. Sorry. Natural between shock. Oh, well, this means the internal connected sum. This means the boundary connected sum. So we have two manifolds with boundary. We can just add one handle on the boundary. That's the boundary connected sum. You do connected sum on the boundary. Okay. Yeah. So so this four-dimensional light bulb theorem needs a modification, and so actually the first disk is just a standard disk sitting inside the first vector, and the second disk is obtained by adding a self-referential disk to the first disk. Here gamma travels a non-trivial loop in the second vector. You can see that the second vector has a non-trivial S1 direction, so we let gamma travel along that loop. Okay? So that's the self-referential disk. Okay, then maybe maybe let's talk a little bit about the Dex invariant, where it is. So first, the Dex invariant is really defined by Dex like 50 years ago, in a very general setting. But for our purpose, we will focus on Dex invariant for loops of embedded arcs. Okay, so let's consider the space of embeddings from I just means 0, 1 interval, to M. M is a full manifold. Okay, so we want to study the space of all arcs with fixed endpoints. Okay, with fixed endpoints. And first of all, this space has a fundamental group. We want to study the fundamental. Well, for dimensional reason, the pi 0 of this space is not so interesting. But it's basically just determine the pi 1 of M, so it's not so interesting. But the fundamental group starts to be more interesting. So let's consider its fundamental group. This fundamental group has a map. This space has a natural map to the space of maps from I to M. Okay, so we don't care about embedding, we just consider maps. And it turns out that this group, the second group, is actually isomorphic to the second homotopy group of M, pi 2 of M. It's not hard to, you can think about why. But anyway, so we want to study the kernel of this map. Namely, if we have a loop of embedded arcs which are trivial as a loop of continuous maps. Okay? Basically, we want some invariant. Okay? So given such loop, this group is called a Dex group. So it's a subgroup of the fundamental group of embedded space for arcs. And now, given element here, we have the following commutative diagram. So let me explain this commutative diagram. First of all, this element is represented by a loop, right? So we have a map from S1 to the embedding space. Okay. Now we see that this belongs to the kernel of this map. So that means if you include this embedding space into the space of all maps, this element is now homotopic. And that means you can extend the map to the two-dimensional disk. Right? So you have this outer commutative diagram. Okay? But now you can insert a third object in the middle. So this is the space of immersions. Okay? Immersion, remember that immersion of the submanifold just means that the tangent map is injective everywhere, but we don't require F itself to be injective. Okay? So there's an intermediate object, immersion. Okay? Then the immersion space of immersion is actually well studied by the work of Hirsch and Smale. You can prove that using some obstruction theory. You can prove that you can always lift this map to here. In other words, you don't just get a D2 family of continuous maps. you get a D2 family of immersed arcs. Okay? So every point here give you an immersed arc. Okay? Now, another useful fact is that this is a stratified space. The space of immersion is a stratified space, and the open strata, which is the top dimensional strata, is the space of embeddings. And there are some lower dimensional strata consisting of like immersions with small with singular points. Okay, but one useful fact is that the only codimensional 2 strata, there are no codimensional 1 strata. The only codimensional 2 strata consists of those immersions with a single double point, namely every immersion is like this. So this is a codimensional 2 phenomenon. As you can see, this you can basically, okay, in 3 dimensions, you can perturb this double point in a single direction. But in 4 dimensions, you have more freedoms to perturb this away. So this happens in codimension 2 situation. Anyway, so, and from this, we see that if we choose this gamma tilde careful enough, you can ensure that for all but finitely many points in the disk, you get an embedding. You just get immersion for finitely many points in the disk, and for each of them has a single double point. So basically, it's like, yeah, we have a disk, and there are some discrete finitely many points of disk that correspond to some immersions. All the other points are regular embeddings. Okay? So this is the picture. And now for each of these embeddings, you notice that there is a loop here, right? There's a loop. For each of these immersion, you get a loop. And this loop represents an element in the fundamental group. Of course, the loops are all based at different points. You need to use part of the arc to change the base point to the same one. Okay? Anyway, that's some details. So basically, I want to say that each double point gives you an element in the fundamental group, and each double point, there is a canonical way to determine whether it's a positive double point or negative double point. There is a way to define a sign here. So then what do we do? Okay, so we just take the sum of all these elements in the fundamental group, okay, by the plus minus sign, and this gives us a element in the group ring of the fundamental group, right? So this group Z pi 1 is just a group ring of the fundamental group. It consists of formal linear combinations of the group element with integer coefficients. And we need some modifications here. First, we need to throw out the unity, the identity element. We need to throw it out. Namely, we ignore all those contractible loops. We don't consider them. That's the first modification. And second modification, we need to portion out by some action of the third homotopy group. Okay, there are some. As you can see here, we make a choice of gamma tilde. Okay? If you choose a different gamma tilde, they will differ from each other by some element in pi 3, and you can estimate the difference. And it turns out that if you portion out this possible ambiguity, you get a well-defined invariant called a Dex invariant. Okay? So this Dex invariant is an invariant, and it turns out Dex proves that this is an isomorphism. So Dex completely compute this group. Basically, it just comes from counting like loops created by double points. Okay? Yeah, questions? Oh, sorry, you know what? Yeah. Yeah, this is okay. Both are infinite dimensional spaces, but the codimension still makes sense in a certain way. It's like, yeah. You can make that. Yeah, for example, you can make everything to the Banach manifold. Oh, sorry, what? Which? Capital pi? Capital 0, 1 interval. From 0, yeah. Huh? K not fixed. It depends on like the number of immersions appears in your disk family. Yeah. So there are finitely many immersions in your disk family. K is the number. Yeah. Okay. Yeah. All right. So Gabay used this invariant to define to show that two disks are not are homotopic but not isotopic. So how did he do that? So given two disks, we can, if you have a two-dimensional disk, you can do the following funny thing. You can decompose the disk into a one-dimensional family of embedded arcs, something like that. Okay, so basically you can decompose this two-dimensional disk into a whole family of embedded arcs. So IT just means for each T you get a one-dimensional disk, okay, or just interval. Okay. Then, so if we have two embeddings, we get a path from this 0, 1 to this arc embedding space, because you can just restrict this embedding to the T slice. For example, you can restrict the embedding to a single slice that give an embedded arc. So you can treat this embedded disk as a path of embedded arcs in the four manifold. Of course, some information is lost in this by doing this, but you can still get some information here. Okay, so we get a path in the space of embedding space in the embedding space. We can do this similarly for the other embedding, gamma 1. Then we have two passes, okay, in this embedding space. And these two passes have the same boundary because D0 and D1, they are equal each other on the boundary. So these two passes, you can imagine two passes in the space of embeddings with identical endpoints. Okay. Then what can you do? Okay, so moreover, the fact that these two disks are homotopic to each other relative boundary means that if you compose these two passes, you get a loop which is contractible in the space of mapping, in the mapping space. Okay? Namely, you get an element in the DEX group. Okay? Remember that DEX group is the kernel of pi 1 of embedding to the pi 1 of mapping space. Okay? So this is, you get a contractible loop. Well, you get a non-trivial loop here. And then you just define the DEX invariant of these two disks as the DEX invariant of the corresponding arc family. You get, this is a loop of arcs, right? We just define its DEX invariant. So you can define the relative DEX invariant of these two-dimensional disks. Okay, and this turns out that this is correct invariant actually to generalize the four-dimensional Liebhaus theorem. Actually, Kosanevich, Tachner, they proved that. What did they prove? They proved that two disks are homotopic if they have a common geometric dual and the relative DEX invariant. Two disks are isotopic if they have a common geometric dual and their relative DEX invariant equals 0. So that's the only invariant we need to add to modify this Liebhaus theorem to disks. And okay, and next we want to generalize the DEX invariant not for disks. We want to study closed embedded surfaces in four manifold. Okay, so we don't want the manifold to have boundary, and so we consider the special case that the manifold is a product between a sigma and S2. Sigma is a closed surface of genus greater equal than 1. Then now you can study the following thing. You can study, sorry, I missed something here. You can study all embeddings from sigma to M with a given homology class. So this is a very large set. Then we want to classify elements in this set up to isotopy. And to state the invariant, let's introduce another set, which is just pi 1 minus 1 up to modulo conjugation. So this is the set of free homotopy class of non-contractible loops Now, what's our result? Basically, what we prove is that there exists a Dex invariant, a relative Dex invariant, which goes from this product sigma D cross sigma D to ZC. So this is the group ring of Z, such that if two embeddings are isotopic to each other, then their relative Dex invariant equals 0. This Dex invariant is additive. And if you have a diffeomorphism which is homotopy to identity, then actually the Dex invariant is unaffected. It's invariant under this homotopy. And of course, well, up to this point, you can say, okay, why don't we just choose 0 map and map everything to 0? Well, it's okay. So the first point is that this is indeed a non-trivial invariant, meaning that if you take any element G, you can construct two embeddings which are related to each other by some diffeomorphism F, and they are homotopic but not isotopic because they have non-trivial relative Dex invariant. So, and F here is the so-called barbell diffeomorphism, which I will quickly describe. Okay, so yeah, so the idea of proof of this theory is that, okay, it's actually a quite natural idea. We just pick a handle decomposition, or you can just say CW decomposition of the surface. You have a single 0 cell, two G1 cells, and a single 2 cell. Then after isotopy, you may assume that the two embeddings are equal each other on the 0 cell and the 1 on the 1 cell. Then what do? You just remove a tubular neighborhood of this one skeleton. Then you get two embedded disks in the complement. Then you just evaluate the Dex invariant for disks. Okay. The true difficult point is to prove that this is well defined, meaning that it doesn't depend on the isotopy. At the beginning we do an isotopy so that the two embeddings are equal each other on the one skeleton. So how to prove that such isotopy do not change the final result? It's quite possible that you choose a different isotopy and give you a different answer, right? So that's the key point of the proof. But for time reason, I don't have time to explain it. Okay, anyway, so that's the result. And there's some applications. For example, if we consider this product manifold, we define an important object is mapping class group MCG. So it's just defined as the path component of a diffeomorphism group, or you can say it's just a diffeomorphism on M modulo smooth isotopy. Okay? So this is an important object to study in manifold theory. And one corollary is that there exists a surjective map from surjective group homomorphism from MCG to Z infinity. So which remains surjective even if you pass to the subgroup of diffeomorphisms that are homotopy to identity. So in particular, that means this MCG, the mapping class group of M, is infinitely generated. Okay? So this is, for example, this is something not so trivial because if you think about mapping class group of S2, it's just a single element. Any orientation, this is proved by Smale. Maybe even earlier, yeah. So Smale proved a stronger result. The diffeomorphism group of S2 is homotopy equivalent to SO3. So, yeah. And if you think about the mapping class group of the surface, it's also finitely generated. It's actually generated by 3 or 4 Dan twists. So, but if you take the product of these two pieces together, you get something infinitely generated. And the idea of proof is that we consider this standard embedding. Then we just define this surjective homomorphism by taking the relative Dex invariant of this I0 and its image under F. Okay? Yeah, of course, we need to prove that this is we will see that we can construct many interesting Fs such that this map becomes surjective. Okay? And one corollary is that we are able to generalize the Liebov theorem for closed surface for in this specific manifold. Yeah, I think it should be true like almost for every manifold, I would say. Yeah, but so far we don't know how to prove it. Yeah, we have a project trying to prove it for like a product of 3 manifold with S1. Barney-Gabay, they prove the result for S1 cross S3. And they also prove it for hyperbolic form manifolds. They show that for hyperbolic form manifold, the mapping class group is also infinitely generated. Yeah, also using techniques related to configuration spaces. So this is in sharp contrast with low-dimensional situations. Okay. Yeah. All right. So yeah, yeah, I still have like 5 minutes, so I guess I might need to speed up. Anyway, so this is some specific construction of diffeomorphism. This is called a barbell diffeomorphism we used in the construction. Actually, it was introduced by Barney-Gabay. So what's a barbell? A barbell is just a boundary connected sum between two copies of S2 cross D2. And you can also think it as like the complement of two standard arcs in 4-dimensional D4. Then there is a very interesting diffeomorphism called barbell diffeomorphism. Intuitively, it sends these two disks to something like this. I will skip some details of construction here, but basically there is some very interesting diffeomorphisms on this simple manifold. Okay? It's called barbell diffeomorphism. Okay? All right, so it sends the blue piece to this and the red piece to this, and they wind each other. The middle this is a hop link. So they link each other in the middle. All right, and now we need to consider specific so-called self-referential barbell. So what's that? So just now I said there is a diffeomorphism on S2 cross D2, and how to generalize it to arbitrary manifold M. So now suppose we have a manifold M. What do? We pick two embedded spheres, S0 and S1. Okay? S0 and S1. Both with self-intersection number 0. And then we take an arc, gamma, connecting these two spheres. If we do this, it's not hard to prove that a tubular neighborhood of this guy is diffeomorphic to the barbell I just mentioned. So in other words, you can just take a tubular neighborhood of this guy and apply the interesting barbell diffeomorphism I just mentioned. Okay? In other words, what you need to do is to find two spheres with an arc connecting them. And now, okay, as I said, you just take the barbell diffeomorphism and extend it by the identity on the complement. Okay. Now we set M equals sigma cross S2, and the first S0 is just S2, and the second one is obtained by adding a self-referential disk. Oh, sorry, not self-referential disk, I should say. Second one, let me draw another picture here. So basically, the first S0 is like this. And what about the second one? We take a 3-dimensional sphere, then we take an arc which intersect this and this. This is gamma. And this S1 equals boundary of D. So remember this configuration we have just seen this just now, right? So we take a 3-dimensional disk, we take the boundary to be S1, and we just take an arc that passes through the interior of this disk and goes to and connects the boundary of these two spheres. And this is called a self-referential barbell. Okay, so you can then, as I said, whenever you have two spheres with self-intersection number 0 and you have an arc connecting them, you can construct a barbell diffeomorphism. So that gives us a lot of diffeomorphisms on this M equals sigma cross S2. And using Dex invariant, we can prove that they are all linearly independent in the mapping class group. So, we can choose different gamma because this guy has a large fundamental group. So we can let this gamma to travel like in any complicated loop in the manifold. Okay? Yeah. So using Dex invariant can prove that all these linear diffeomorphisms are linearly independent in the mapping class group. Okay. I guess my time is almost up. Let me just use the last minute to talk about some application in symplectic geometry. So a symplectic form is a closed two form, which is nowhere, whose square is nowhere vanishing. I'm talking about symplectic forms on four manifolds, and so we can consider the space of all symplectic forms in a given homology class. Okay? We denote this space by SA, and a path in this space is called an isotopy of symplectic forms. And so a well-known open question is about the uniqueness of symplectic forms on four manifolds up to isotopy. Namely, does there exist a closed four manifold such that SA is not connected? Okay, you can also ask this question: does there exist M such that SA is connected? Well, basically, we know nothing about connectedness of this space. Yeah. And so as one application, we prove the following result. If you have a root surface, which is just a sphere bundle over a Riemann surface of genus greater or equal than 1, then this space always have infinitely many path components. Namely, on this specific four manifold, we have infinitely many symplectic forms, which are not isotopic to each other. Okay? So the idea is to take a standard symplectic form and pull back using the barbell diffeomorphism I just mentioned. And to prove that the resulting symplectic form are not isotopic, we need to use a little bit J holomorphic curve theory to show that if these two were isotopic, then beta n would be isotopic to identity. But this is contradiction with our previous result that beta is infinite order in the mapping class group. So yeah, I think that's all I want to say. Thank you very much for your attention.
Okay, thanks for the wonderful talk. So, do you have any questions?
Regarding the last theorem, is this result related to the McDuff conjecture about the road surface? I mean,
McDuff conjecture slightly, well, it's related, but not in a direct way. You mean the symplectic mapping class group,
yeah.
that conjecture? Yes, I mean, if McDuff's conjecture is true, then there is an easier way to prove this result. But we'll basically prove a weaker version of that conjecture. So McDuff conjecture states that basically, like the symplectic mapping class group of a root surface is blah blah blah. We didn't prove that conjecture, but what we prove is that you consider the map from symplectomorphism to diffeomorphism, and if you consider the image of this group, it's exactly as conjectured by McDuff. So it's a weaker version of McDuff's conjecture.
Thank you.
Any other questions? So it seems that you study two notions of relation of maps. One is isotopic, another one is differed by diffeomorphism. Mm-hmm. So it seems that this isotopy is weaker than another
one. Isotopy, you mean isotopy of surfaces or isotopy
I mean, you study the homotopy type of the fiber of the diffeomorphism. That is this is somehow weaker than the relation modulo by diffeomorphism.
Yes, right. If two, let's say, if two submanifolds are isotopic to each other, then you can find a diffeomorphism that stands one to each other, but the inverse is not true. So being like two submanifolds being a diffeomorphic is weaker than two submanifolds being isotopic.
That is okay. So for example, in the case of spheres, maybe S4 something, then what is the homotopy fiber you define there?
Okay. You mean the space of smooth structures here?
Yeah. Just what is the relation between the actual smooth structures?
Let's different. Those are two different questions. I think here I'm thinking about. Okay, so let's see. Here I'm taking the space of smooth structure that are diffeomorphic to a standard smooth structure. Okay, so basically this question is asking if we just ignore those possible exotic smooth structures on S4, even focus on the standard smooth structure, are there non-trivial families of smooth structures on S4? So this is a family version of what, yeah, but this is now is known, like for example, I think it's known before, even before Watanabe. So we know these two spaces have very different homotopy type for S4.
Oh, so they are different questions.
Yeah.
Different.
They are different questions. Yeah, basically, yeah.
Okay. Okay. Next speaker. Okay.